All right, so let's jump back into here. Friday, we left off working through some of these reactions, and we were talking about that reaction in letter B, saying that uh, that inversion of stereochemistry was indicative of a SN2 type reaction. All right, and so you'll see the same thing in C. Right, what set of reagents would you use for C? Let me go back and refresh you. These are our choices up top. HX, X can be any halogen except fluorine, thionyl chloride and pyridine, and then PBr3. So what would you use here? For letter C.
Would you use PBr3?
Oh, hold up, let me turn my volume up. Go ahead, say that again.
Would you use PBr3?
Yes, you could use that. Right, you're looking to swap out the hydroxyl for bromine, and again, you can see the stereochemistry is inverted. Right, which means that this also went through an SN2 type mechanism. Right. What about D?
Would you use, what is it? Dia something chloride with the purine.
I or something? I'll take that. Yeah. So here you have why did you pick that? Let me ask that question.
I said it's because the alcohol is primary.
Excellent. Primary alcohol. You need a reagent that will facilitate that conversion and not involve a carbocation intermediate or whatever. So you want to use thionyl chloride and then pyridine. Good. All right. What about E? Whatever you pick, tell me why you picked it.
Would it be HBr?
Good. Why'd you pick that?
The alcohol is tertiary.
So tertiary alcohol. And again, these methods are not happens by happenstance, right? All this stuff, all these methods are developed over time and with experimentation so that you have tools to convert, again, alcohols into alkyl halides. And depending on the type of alcohol you have, you can pick your reagent, right? So you're not trapped in a box with only one way to do something. All right, let's look at number 3. We didn't do the substitution pattern or the substitution mechanism for A or D and E. So what do you think about A? If you use HBr, what type of substitution is going to happen? Because all of these are substitution reactions. If you use HBr on a tertiary alcohol, is it SN2 or SN1?
SN1.
It's SN1 because it goes through that carbocation intermediate. All right. What about D? If it's a primary alcohol and you're substituting with thionyl chloride, what mechanism is that going to go through? I think we talked about this.
Is
Go
it
ahead.
SN2?
It's SN2. I think we talked about this somewhere up here. What can't remember exactly where we talked about it, but I know I gave you that a primary alcohol will never do SN1 and a tertiary will never do SN2. So this is SN2 and this is SN1. I may have just said that verbally and not written it down. All right, let's go to the next set of well, no, we got one more question up here. It says, draw reaction energy diagram for A and C. So for A, if it's SN1, we're not even gonna go through like the rigmarole of determining the energy and all that. How many steps is this reaction? The total reaction now, not just the rate determining step, which is the loss of water. Right? How many steps happen in this mechanism? If you got to go back in your notes, go back in your notes and look. Because the reaction itself, remember we said it proceeded through a certain number of steps, and we did the energy diagram for it.
Is it 30 steps?
What's the first step?
Proton transfer.
Good. Proton transfer. What's second step?
Loss of leaving group.
That's your rate determining step. What's the third step?
Attack of the nucleophile and electrophile.
So the attack of the nucleophile on the, I'm gonna say the carbocation. That you're right, it is the electrophile, but I'm gonna say that it's the carbocation intermediate. Right. So for that reaction energy diagram, how many humps would it have? If the x-axis is time and the y-axis is energy, what would it look like?
Well, I had 3 humps in the diagram.
So it'd be a fast step.
Mm-hmm.
The second step is loss of leaving group. So that's going to be endothermic. That's going to be a slow step with a high activation energy, and then a fast step at the end. Right. So this is step 1. This is step 2, and that would be step 3. You got three different transition states, 3 different activation energies, right, and 2 intermediates. Right, everywhere in between a step is an intermediate. Right, everywhere on each one of these curves, at the top, the highest energy point is a transition state. Just trying to jog your memory. Right, and the gap between, let me switch pens. The gap between the transition state and the starting material is your activation energy. And the rate determining step is always going to have the highest activation energy. All right, let's do the same thing for what did it ask for? A and C. What is C? So we already know that C is SN2. So the rate determining step is it stepwise or concerted? Help me out.
Concerted.
Concerted. Good. So how many steps are in that reaction? Sorry. I'm trying to shrink this so I can make that diagram bigger.
Is it 2?
2 steps. What's the first step?
Proton transfer.
Okay, let's see. Is there a proton transfer step in the PBr3 reaction? I think it's just the OH directly attacking.
Yeah.
Yeah, so for this reaction, there's no proton transfer. There is for the first step, there's going to be attack of OH. So it's kind of like a substitution in the first step, because when the OH attacks, you lose a bromine. And then the second step, it will be bromine attacking the phosphorus oxygen intermediate. So this is the rate determining step. All right, so what would the diagram look like for that?
Would you have a fast step and then the slow step?
Yeah, so the first step will have to be faster than the second one, right? Because the second step is rate determining. The rate determining step is always the slowest step in a mechanism. So if the first step is, let's say it's fast and exothermic, we can draw it like that. Second step, higher activation energy, we can draw it like that. All right, and again, you got transition states here, one intermediate, but there's no intermediate for the second step going to the product. That's why we can say that the second step is concerted. So this is my starting material. My product's on the other side. That intermediate comes from that phosphorus oxygen reaction that happens in the first step. But there is no intermediate from this to the product, because it's all concerted. All right. All right, let's go to the next part of this. Let's answer this question. It says rank the carbocations below in order of decreasing stability. Well, 1 is the most stable, and since there's 4 of them, 4 is the least stable. Which one is going to be 1 out of those 3 carbocations, out of those 4 carbocations? And what is the trend again for carbocation stability?
Would the methyl be the least stable?
The methyl will be right here.
Yeah.
The
would that
worst.
be the worst. Yeah.
All right, so that's going to be 4. Is that right? Because 1, it says 1 is the most stable. So, and we're ranking them from 1 to 4. So this is the worst one. What's the best one?
The one on the tertiary carbon.
Tertiary one. Good. All right. Does anybody remember? Let me pause right here. And again, jog your memory back to part 1. What is the stabilizing factor for that tertiary carbocation? Like, why is that so stable compared to the other ones? Anybody remember that from part 1?
Is it induction?
So it is. It's a type of induction. Yes. We gave it a special name, but you're right. It is induction from what? Help finish that, because you're right. You're not just in the ballpark. You're eating a hot dog right now. So finish that.
Yeah.
You're right that it's induction. So tell me what induction is.
It's like isn't it like something to do? It's something like with delocalizing the electrons or something like that.
Yeah. So in this case, if you have a carbocation on that tertiary carbon, and it's bonded to a methyl here and a methyl here and a carbon over here, which is CH2. Which way is the induction going to go? You're right. Which way is that dipole going to go toward where that plus charge is? What is it going to go? Are electrons going to go toward the charge or away from it? It's a positive charge now.
They're
So is
going to
it-
go towards the charge.
You're going to go towards the charge. Good. So you're going this way. Boom, like that, and like that. The more carbon-carbon single bonds you have around that charge, the happier it is, right? Because all those electrons in those bonds are going to get pulled towards that positive charge. We said it was, we gave it a special name. We called it hyperconjugation, which is really just a fancy way of saying induction. Right, but you're right, it is induction. It's a type of induction where the plus charge is creating a dipole between the carbon where the plus charge is and the carbon is bound to. Great job with that. All right, what about which one is going to be number 2 and which one is going to be number 3?
Is the this secondary number 2?
Yes. This is going to be 2, and then this would be 3. The second worst one, primary, right? If you notice on that primary carbon, this is a CH2, right? There's very little induction happening here. One carbon-carbon bond with electrons in it that's able to stabilize that. But in the secondary, you can see that there's a little bit more ability to do that hyperconjugation because you have a 2 carbon-carbon bonds around that positive charge, right? So yeah, all that's just, again, it's just review, because that understanding these carbocations helps us to understand these mechanisms, because a mechanism that proceeds through a carbocation intermediate is either going to slow down or it's going to speed up based on how stable that carbocation is, right? And the stability is always based on how it's substituted. If it's tertiary or secondary or primary, or if it's a methyl carbocation, which is the absolute worst. All right, let's do this next reaction. And yeah, let's do this next reaction. All right. All it's asking you to do is put the arrows in. So what is it asking you to do in that first step? You have a proton source and you have an alcohol. I don't know if you can see the electrons on that, but I'll put them in. They're kind of faint. All right, here's a rule of thumb. Anytime an OH group, hydroxyl group is in the presence of a proton source like this, right? We know that that's H something, HCl, HBr, HI. Anytime you have a OH in the presence of a proton source, is going to do proton transfer. Right, that happens readily. You put a proton in the presence of OH or an oxygen, period. That's going to readily happen unless that oxygen is tied up in resonance, like with a carboxylic acid. But you just put a alcohol in the presence of a proton source, it's going to get protonated. And it even gives you that here. It says that you get a protonated alcohol. What would that look like?
Would the oxygen have a positive charge on it?
You'll have a positively charged oxygen. Good. And what do we call that? That positively charged water, because that's what it is. It's like it becomes a water molecule. What do we call it? Anybody remember? I think I gave you a term for that on Wednesday of last week or Friday, one of them, maybe Wednesday.
Is it hydronium ion?
Yes, yes, thank you. It's called a hydronium ion. Right? What's the purpose of that proton transfer? What do you think is going to happen now? Right? It's kind of giving you right here. It says the water acts as a leaving group, but let's go back to here because we didn't do what it asked. It asked us to put curved arrows in. So how would you show the proton transfer using a curved arrow depiction or illustration?
With the one of the lone pairs on the alcohol attack the proton.
Like that?
Yeah.
Not like that with that ugly arrow, but like that. That's even uglier. But you get the point. Yes. When we did this in part one, whether you took me or Abdallah, we studied acids and bases. We both talked about the same stuff. What is it like? How do you determine the flow of electrons? Like, how do you determine where to put the end of the arrow and where to put the head of the arrow? Like, what determines that? Somebody besides Tia and Taj, the tag team duo, somebody besides them tell me that. Did somebody put something in the chat, or is that just a thing? All right, anybody? We got 22 people logged in besides me. How do I know where to start the arrow and where to end the arrow?
Don't you determine the arrow location based off of what's being attacked and where the electrons are coming from?
You do. You do. So when you say where the electrons are coming from, what do we call that? It can be one or two things, right? It can be a base or it can be a nucleophile. But the arrow is always going to originate wherever you're at the source of your electrons, right? So electrons always go, good job, by the way, from source to sink, right? Every time. So that's how I know to push towards the proton and not the other way around, right? This is never going to happen. And the reason is because the arrow indicates the movement of electrons. If it's H plus, it doesn't have any electrons to give away. So you can't push those back towards oxygen. Every time I put an arrow in, it means that electrons are moving. So you can't move electrons from an atom that doesn't have electrons to give away. All right, let's go to here. All right, how would we, with curved arrows, depict water leaving as a leaving group? Think about it in terms of, everything is really, when you talk about breaking and making bonds, everything is in terms of dipoles, but think about it in terms of dipoles. If that oxygen is positive, which direction, and this is a unimolecular process, there's no electrophile coming in to knock out the oxygen and replace it. What direction would the dipole be in for that carbon oxygen bond right there? This one. If that oxygen has a plus charge on it, where do you think the electrons in that bond are going to be pull towards it? Is it going to be pulled towards carbon or towards oxygen?
Oxygen.
Towards oxygen, right? Anytime you have a positively charged atom attached to an atom that's neutral, the electrons in the bond are going to be attracted to that positive charge because electrons by nature have a negative charge. So when I show this bond breaking, right, which direction should the arrow go? I got two choices.
The carbon.
I can show it going this way, which is totally contrary to what the dipole is saying. So that's not going to happen. The actual reaction or the bond breaking process is going to happen like this, right? Where those electrons actually get transferred onto oxygen, right? So you're going to lose water. Right, if you notice right here, there's one pair of electrons on oxygen. Over here, two pairs. Uh-oh. Right, so it'll be water plus what? Just telling you right here what should be here.
Carbon.
So it's it's water plus this carbocation. Right. And this is again just the basic mechanism for the reaction of HX with the alcohol. You protonate, you lose the leaving group, you make a carbocation, and then the carbocation gets attacked by an incoming nucleophile, whatever the halogen was on that acid. Go ahead, Tia.
I have a question about the hydronium ion, the last part.
Mm-hmm.
I see that it has two lone pairs. Oh, never mind.
Yeah, that was my fault. You talking about where the plus charge was?
Yeah.
No, that's my fault. It's really, I was trying to say that it was water plus the other thing.
Okay.
I'll just do this. So I'll just say water and instead of plus. Yeah, my bad. I knew that was what you were about to ask because when I looked, that's why I erased it, the plus sign and tried to move it. All right, questions about that mechanism, about the arrows, about anything? All right, so with this last problem, let's see what we can do with this. So it says bonus, but this is not a bonus question. This is when you turn this in, you're gonna turn the whole thing in. It says predict the products of the reaction below and use curved arrows to show a mechanism. All right. So with this particular reaction, let me show you the product. And then we're going to go back and work our way through it to see if we can figure out where it came from. All right. So let's say this is what would the expected product be here? What would you expect the product to be? Here's the OH group. We know that HCl is a way to convert that into a alkyl halide, to an alkyl halide. What would the expected product be?
Would the Cl replace the alcohol?
Just a straight up substitution between the OH and the alcohol. I'm sorry, and the halogen, my bad. This is the expected product. Now, what's observed is this. right, and let me, I'll leave it there. This is the observed product, where the chlorine is on this carbon. All right. So let's go through the mechanism. Let's go just step by step. We're going to show every step. And then when we get to the carbocation, we'll be able to figure out what happened and why we don't see that expected product. Or let me just say this, if you see it, you see very little of it. All right, so let's go through the mechanism. And I'm just going to copy this right quick. All right, so this is plus, what are we using, HCl. All right, somebody tell me what happens in step one. I know it's redundant, but reps are the key to retention, being able to retain the information.
Proton transfer.
So you're gonna get a, sorry about that, proton transfer that happens like so. Is that right?
Mhm.
So then from that, let me move this over some. All right, so from that step, that proton transfer step, we're going to get this intermediate. Anybody not agree with that? All right, so that's my intermediate. And what's the next step after that?
Isn't it the leaving group?
Good. The leaving group, which is what in this case?
The hydronium ion.
Good. Water. So hydronium ion. So I'm gonna lose my leaving group. And again, anytime I break a bond between two atoms and it's heterolytic, meaning one atom is going to take both electrons, the atom that's more electronegative is going to get those electrons, right? So in this case, it's going to be oxygen. So I'm going to break that bond like that, give those electrons to oxygen. And then in doing that, I'm going to make a carbocation intermediate, which is the hallmark of this reaction, right? That's the key characteristic of this reaction, is that you get a carbocation intermediate because it's a SN1 type reaction. So this carbon becomes positive, right? And this is plus water. I'm gonna put this in brackets. Right, so this is again, we're just using HX to convert an alcohol into an alkyl halide. Right, so that intermediate is common in this reaction. Now let's look at that. And then this will be, keep in mind the chlorine we lost here. Put some electrons on it. Right, just hanging around waiting for his chance to shine. Right. So here's the question. Very interesting question, by the way. The expected product is with chlorine attacking that plus charge, but the observed product is here. So something had to happen in order for that carbocation to end up on that other carbon. All right. So let's think about that. I don't know how much of this Abdallah talked about, but I know we talked about it in part 1 in my section. So, but it's okay. It's something that that we're gonna discuss now. All right. So you have in this case, a secondary carbocation, right? And that secondary carbocation is adjacent to a tertiary carbon. All right. So this intermediate, in order for this product to be predominant, so we're going to call this the major product. In order for that to be major, what do you think has to happen? Like for chlorine to attack that carbon, where it is in the major product, what would that carbon have to have in order for chlorine to be able to attack
Hy-
it? Think about chlorine as the nucleophile. That carbon would have to be electrophilic. So what would it have to have in order to be electrophilic?
a base.
Say that again.
A base.
Not a base. If chlorine wants to give a pair of electrons to an atom, what does that atom have to be? It has to be electron poor, right? It's got to be able to accept a pair of electrons. So for that carbon down on the end to accept a pair of electrons, wouldn't it need a charge on it, like a positive charge or some kind of dipole to be able to do that? So
Yes.
so the question now becomes, how do we make that carbon susceptible to attack? Right? I'll buy anybody who can tell me how to make that carbon positive. Look at the product and look at the structure. If you can tell me how to make that carbon on the end, that tertiary carbon, become what actually is quaternary as it is, but it'll become tertiary. If you can tell me how to do that, I'll buy you lunch today. And you can ask anybody who took my class before, I'll buy Happy Meals. So somebody help me out.
What?
I'm just going to go ahead and copy this and put it in a better place. So we can expound on it. Right. So let me jog your memory, because I feel like I'm beating a dead horse somewhat. All right. So when you have a positive charge like that, and you have a carbon adjacent to it that's able to give you a more stable positive charge, then sometimes you can have a rearrangement that occurs. So when we do rearrangements, they don't just happen like randomly or by happenstance. Everything that happens in chemistry is from a energetic perspective, right? So you have like something going from higher energy to low energy. That's the goal. That's the goal of every chemical reaction doesn't give you that. So sometimes you have to use catalysts. Sometimes you have to use increased temperature and different factors like that. But everything is always trying to get to a lower energy state. That's the universe at work. So if you have a secondary carbon like this one, and it's adjacent to a tertiary carbon, well, actually, let me not say tertiary because it's not, it's got 4 groups on it. It's next to a more substituted carbon. I'm just gonna say more substituted. It's actually a quaternary carbon. All right. This can do what's called a methyl shift. Right. So one of these methyl groups is actually going to move. I'm just going to write this as the one that's moving. So it's this carbon and both electrons are going to move to here, where this plus charge is. The whole thing. Right now, the other intermediate that you get from that would look like this, right? So the CH3 is now here. Right, and then over here, that carbon becomes positive. What's the difference in those 2 carbons? What type of carbocation is that I just made?
Tertiary.
It's tertiary. Is that good or bad? Going from
Good.
secondary to tertiary.
Good.
It's excellent, right? This is a more stable carbocation. Come on, handwriting, tighten up. Right, so when you do a rearrangement, it's normally done in terms of achieving a more stable intermediate or a more stable product, right? So in this case, you go from a secondary carbocation. I'm just going to abbreviate this as C+. So this undergoes rearrangement. And the conditions have to be right for rearrangement to happen. Right, so you go from a secondary carbocation to a tertiary carbocation. Right, so now it's this intermediate that the chlorine attacks. So that's negative. This is going to attack right there, and that'll give you the observed product. All right, so if you have a secondary carbocation and it can rearrange, or even if you, by some occurrence, you get a primary and it can rearrange, right? You can do rearrange either 1 or 2 ways for carbocations. You can do a methyl shift, which we did here, or you could do a hydride shift. Right, where you, instead of shifting a methyl group, you shift a hydrogen with a pair of electrons with it. All right. What was I getting? There was something else I wanted to say about this. What was it? Oh, okay. Let me ask this question. What's faster? Attack of chlorine on the secondary carbocation or rearrangement? Keep in mind, this is the major product.
Rearrangement.
The rearrangement will have to be faster. Very good. Excellent. Put your cash app in the chat.
Okay.
The rearrangement will have to be faster than the attack of chlorine on that secondary carbocation. It has to be. Otherwise, this wouldn't be the observed product, right? So rearrangement has to happen faster than direct attack. So let me write that here. All right, so rearrangement must be faster than attack on the secondary carbocation. That's why you see that observed product. And the whole purpose behind rearrangement, again, is to go from a less stable state to a more stable state. All right, any questions about that? No questions. All right. We're gonna stop here. We'll pick up on, I'm gonna send you videos today for Wednesday. We're gonna start a new section on organometallics. And so on the next exam, which will be hopefully end of next week, somewhere up in there, when we take that second exam, is gonna cover alcohol conversions to alkyl halides and organometallics, unless we finish organometallics and fit something else in, but I'm not gonna rush that because the organometallic section is pretty important. So yeah, so we'll take the next exam is gonna be over these two topics. So it's gonna be alcohols to alkyl halides, which is under our umbrella of alkyl halide synthesis. And then what we start on Wednesday is gonna be application of alkyl halides, so ways to use them. We use them to make organometallics, and then the other way we're gonna discuss is in substitution and elimination reactions. All right, so we're gonna stop here. Let me stop sharing, stop recording. Tia, did you have your hand up?